Now, welcome to another RDWorks Learning Lab. I think the title says it all. And today we're going into a journey of discovery. It's one of those loose ends that's been kicking around from day one when I first started to read the manual for this machine. It was total Chinese gobbledygook then, and to be honest, even today, after several translations, it's still Chinese gobbledygook. Now, I'm going to stop there for a minute for two reasons. First of all, I'm going to sing the praises of RDWorks. Now, RDWorks, when I first got it, I wasn't very impressed. As a drawing package, as a CAD package, which it promised to be, it was total rubbish. And I thought to myself, well, here's what you get for nothing. Nothing. But as I came to use the program, I began to understand that it wasn't ever attempting to be a CAD or a drawing package. It was a very, very powerful interface package that converted your design work into machine code that the machine could understand. And without you ever knowing it, magically your designs just appeared in your machine. And as time has gone on, I've got a greater and greater admiration for some of the things that I've seen that RDWorks can do. Some of the tools are a bit clunky, as I've mentioned before, but they're there and they do work. Because I've been bold enough to venture into using my oscilloscope, my admiration has jumped up somewhere near the ceiling. Because I've begun to realise how much RDWorks can do with so little. Now I'm going to explain myself a little bit more, but let me just point this out to you. Look, I've got a biscuit here, which I'm going to eat in front of you, just to make you jealous. But here's a trick that my dad, who was a great philosopher, taught me. He said, son, when you get older, you'll tend to get fat. Here's a trick that you should understand. If you break your biscuits in half, two halves make a whole. And there's no calories in a whole. So you can enjoy it. Right, now, come in close because I want to show you where my admiration springs from. Now here we've got a very simplified sketch of the heart of the machine. We've got the controller and we've got the high voltage power supply. Now obviously the high voltage power supply drives the tube, but it only drives the tube in response to what the controller does and tells it. The problem is, and this is where my admiration comes from, there are only two lines that talk to the power supply from the controller. One of them is this, and I'm going to draw it as a blue line, and this is the light on and off, L on, power on, off. And the other one is this, either we've got this one here, which is the power width modulation, which controls the current level that's flowing through the tube. Now there is an alternative way, so I find out, of controlling that tube with an analog output. Now this lovely China Blue machine only has a power width modulation output, but the light blade machine has got a controller which has both of these options, and the option that's connected up in the light blade machine is this dotted option. Both appear to be doing exactly the same thing, so don't let that concern you. Basically, we've only got two lines into the power supply which are controlling the tube. We've seen those working recently with all my dotty work. This is the red line and this is the blue line. The blue line is purely switching the tube on and off, but the red line is setting the current level that will flow through the tube when it switches on. So that current level, which is determining the power of the tube, is sitting there in the background waiting to pounce the moment the tube is actually switched on. This piece here is part of a block of 10 pixels by 10 pixels, right? And they were all black pixels. So here we've got 10 black pixels side by side, and there is no indication that the power is switching on and off between those pixels. It just runs continuously across that block of pixels, and when it's finished it turns off, and then it scans back the other way and turns on, as we can see there. That's the simple way in which those two lines work. In this particular instance, what we had a checkered pattern. So we did not have continuous dots. What we had was dot, 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 dot. We had a series of dots, 10 of them or 12 of them across. And here we can see, because we've got separate dots with a space between each one, we do get the power turning on and off, and on and off, on, off, on, off. When we get white, we get off. When we get black, we get on and stay on if the adjacent square is black. So there's the other way in which this is working. But of course, again, we've still got the power sitting in the background, ready to pounce at an instant as soon as we get the command to turn the signal, to turn the tube on. Now this red line, again, is sitting here at a specific level all the time, and as soon as this blue line switches to say turn the power on, the current is already ready to flow at a fixed level. So I don't want you to be confused, the power is not on, it's just set to a specific level so that it can drive the tube as quickly as possible. We don't have to wait for the power to come up to a specific level. Now here we're looking at grayscale, and the only reason that this works is because first of all you tick output direct in your scan mode and you set max and min power values. That's what we're looking at here. Here we've got a max power level and here we've got a min power level. And depending on the level of grey that we set in between, and the shades of grey run from 0 to 255, so we've got all those, we've got 256 shades of something, white to black. And we've chosen on our grayscale here certain numbers in this scale. And so what we can see the power once the scan starts, and again here we've got our start point, and the power is already there waiting to start, and away it goes. And then without any change, because here we've got it still switched on, what we've got this time a change of the red line. The current that's driving the power steps up, and then it steps up again, it steps up again. So instantly the power is stepping up to change the output. So this is a different sort of control system. We can take that to its extreme, as we did when we tried to 3D engrave the eagle. And here we can see every scan we get a huge variation in the current as we go across the scan. So the power is able to respond extremely quickly. Those are basically the only two modes of operation that I can see that this machine can perform. It's only got two lines. Everything that RDWorks does has got to finish up controlling these two lines to get an output. So when you look at it in that way, it's an incredibly simple machine. So some of the tricks that RDWorks performs, like selecting all these grayscale levels for each pixel, is quite a phenomenal task. The reason why I'm just going through that summary and showing you this very simple picture is to make you appreciate that we are doing all this again with just two lines. An on-off switch and a power line. Now this picture here brings us neatly on to what we're going to talk about today, because one of the issues that I'd identified when we were doing deep engraving was this rather strange texture that we were getting when we were doing deep engraving. There is something built into RDWorks which you can access through the user menu on the top right hand side, and it's called scanning mode. You will see that there are two options that you can choose. This one is the default option and it's called general mode, and there is an option in there called special mode. Now I'm going to read you this piece of text here from the controller manual from China. Now the first line is reasonable English. If special mode is used, the laser power should be increased. The smaller the speckle percentage is, the more the laser power reduces. The laser power to set should be larger in order to reach the same scanning depth. The purpose to select the special mode is to make the laser light at high power and short time. On the depth scanning, the effect that the bottom is flatter is obtained, but it should be noticeable that if the speckle adjustment is not appropriate, it can achieve this goal. I mean, this is beginning to sound just like gibberish. I haven't got a clue what they're talking about. Speckle adjustment means nothing to me. We've got a couple of negatives there which totally contradict each other. The general impression that I'm getting from this is that you can do something with this special mode to try and get rid of the texture in the bottom of deep cuts. That's the general impression that I'm getting of this. There is one word of warning, and it comes out here. If the high power remains short, the lighting mode will influence the life of the laser. Very strange English, but again, you can interpret that and understand what they're saying is, if you use this mode, you could be damaging your tube. It also then goes on to define speckle size. When the general mode is selected as the scanning mode, this parameter will become ineffective. Well, that's a total waste of English really, because we don't want to know that. When the special mode is selected, this parameter will become effective. The controller will control this parameter among 50 to 99%. Well, whatever that parameter, whatever that speckle size is, it looks as though we can change the size of it. In the RDWorks manual, if you look at many of the direct translations, they talk about exactly the same thing in the same but different words. I'm not going to go through all this gibberish here because it really is just as unreadable as the controller manual. They mention something here. In the special mode, light spots will be treated. What are light spots? Now, your first impression is, look, we've got spots. There are dark spots, there are medium dark spots, and there are light spots. And it's these spots that are going to be treated. When we look at this here, and it says speckle size, you think, oh, maybe there's something fancy going on, and we've got spots within the spot, speckles. Now, okay, I'm being slightly facetious here with the use of English, but you can see how confused you could be when you look at these two descriptions. They don't tell me anything about what this thing here is called FACULA size. They mention light spot percentage here. They don't mention the word FACULA in here at all. They keep using this term light spot. They do mention here working mode of higher power and short period may influence the server's life of the laser. So we've got the same sort of warnings here. We've got two descriptions. One word is FACULA, and so I went to the trouble of looking up what the word FACULA means. Here's the dictionary definition of FACULA: a bright region on the surface of the sun, linked to subsequent appearances of sunspot in the same area. Alternative description is a bright spot on the surface of a planet. Now, its origin comes from Latin fax or fac, which basically is torch. Okay, so we're now talking about some sort of light spot. Maybe with speckles, maybe without speckles, I don't know. Oh, here we are, speckle. Mark with a large number of small spots or patches of colour, the opposite of which is plain. So it's either speckled or plain. All my engineering life I've been able to read technical documents, legal documents, full of all sorts of jargon. But I'm afraid this stuff absolutely screws me. Okay, so I'm an idiot. There are better people around than me that have tried to do a readable translation into English. But hey, I don't think they know what's going on either, because they use the word light spots. Every word of this makes a lot more common sense until you get to things like, while the special mode allows treatment of light spots. Yeah, if the special mode is activated, the power of the laser will be increased in such a way as to reduce the proportions of the light spots. I don't understand, again, and I don't think the person that wrote this understands what they're actually talking about. And I'm not being rude, I'm just saying that even if they do understand it, they haven't told me what they really mean. I think that this word light spots really means beam. I could be wrong, but that's what we're going to try and find out today. Just what all this is about. I'm going to set my machine up and I'm going to risk using the laser in high power mode for even a short duration can reduce the service life of the laser. Do I worry? I don't think so. This is a 4,500 hour laser that's already done about 15,000 hours. I'm not worried if I damage it because, you know, it's already done substantially more than I expected it to do. For the good of trying to understand what this is all about, I've got to do it. Whatever RDWorks is going to do, it's going to have to do it through these two lines. Now, I can't see how it's going to reduce the size of the beam, because if you remember, as a separate exercise, we went through and checked the actual size of the beam. And let me just give you a quick brief reminder of that. Coming out of the tube, the laser tube, we have a beam. And if we look at the energy profile across that beam, we find that it is approximately like that. It's not quite a point, it's a Gaussian curve, but it starts off at nothing at the edge and gradually increases to something big in the middle. Now, if we start going much above about 60 watts, that beam starts to become quite large. The book says 6 millimeters. I've demonstrated to you that there is power out to 12 millimeters. If you get a 40 or a 30 watt tube, you'll probably find that you have truly got something like a 3 or 4 millimeter claim, which actually runs at maybe 6 millimeters at the extreme. Two things puzzle me. How can we make the beam smaller, which is what the claim is? Because we've only got these two lines to play with and I've still got my 60 watt tube. How can it make my 12 millimeter beam down into a 6 millimeter beam? Just by playing with these two wires. I'm puzzled. So that's why this is a real serious journey of discovery. I can't believe what I'm being told will happen, so we'll have to go and find out. Well, here's our next pattern. As you can see, I've got half grey, black, half grey, black. So we've got white, half grey, white, black, white, half grey, white, black. Now we've got these other shades of grey in here. There are supposed to be 5 black ones in the middle there, but we've got all these other shades of grey in here, which is a sort of some strange effect that RDWorks is having. I'm fairly confident they won't come out on the pattern. We're going to set this with output direct, and we're going to set white as the lowest it can go, which is on this machine about 9%, and black as high as it can go at around about 67%. And we'll run at 25 millimeters a second so we can see what's going on clearly. Scan. OK. So we've got our white at 20% power and our black at 60% power and our mid grey somewhere halfway between. So we go white, mid grey, white, black, white, mid grey, white, black. So that's doing exactly what we expected, switching it on, and then the grayscale is jumping up and down in between the on and the off signal on a single scan. Now that means that we should be able to use that pattern to check out this so-called FACULA. Now I've had to remove my picoscope for the moment because I've had to connect my machine up via the USB so that we can make the necessary changes in here. And we go to user and we look down here for common mode. There it is, common mode, scan mode. So the first thing we need to do is to read the machine information back into my laptop here. So we read the information that's there at the moment, and it's set up to common mode, which I would expect it would do. And it then says FACULA size as 98%. In other words, it's the biggest it can be. So the first thing we should do is change that to special mode, and then we'll change this to 50%, which I believe is the lowest that it will go. 50%. Now we want to write it back into the machine. Okay, so now I've got that written back into the machine, and when I do my scan test, we can have a look to see what effect those settings have had on my pattern. Well, the blue signal, which is the switching on and off, is happening at 10 kilohertz. And if we take a look at those red ramps, for every cycle we've got 2 ramps. So that's the 20 kilohertz PWM frequency. With a 50% FACULA, we're showing a peak value of black at about 4.8, 4.7 volts, and 10 kilohertz is the blue signal, and 20 kilohertz is the red signal. And we're now reset the FACULA size to 75%. Still 10 kilohertz. The only difference is the mark space ratio. We're switched on for about 3/4 of the time, as opposed to 50% of the time. So if we go back to 99%, does that mean to say we're switched on the whole time? In other words, this is the off period. At the moment we're on for 75% of this cycle. We will just check that nothing's changed at the top, but I think it's just the frequency, the mark space ratio, that's changed, that's all. And let's put this back to 99. Right. So there's the answer to our question. It's only the mark space ratio between the switch on and the switch off signal. That's all that RDWorks can do. Now how that can affect the beam size, I have got no idea at all. Okay, now I've taken the lens out and I'm going to be blowing on this as it works. And I'm going to run that same program again, which will only take a few seconds. And this might burst into flames, but hey, I've taken the lens out, so the worst that I'm going to do is to smoke the mirror. Okay, now this is 75%. And now 50%. Well, there are the 3 results, and basically what we've got there is 5.2, 5.9 and 6.5. 6.5 down to 5.2. Before I try and explain what's going on and why the hole size changes, I'm going to give you a little demonstration that might help to illustrate what I'm just about to say. I've just lit a match, and I'm very happy to let my finger pass through that match at a fairly slow speed, because although it will burn, the intense energy is not there. It's a gentle heat. It's enough to set fire to paper, but it certainly wouldn't burn through steel. Now, do you think I'm stupid enough to do the same thing with that? I think it's pretty damned obvious why not, because if I pass my hand through that at the same speed, I would do myself a lot of damage, because there's a lot more intense heat in there. That gets up to probably over 1000 degrees C. Now what comes out of our laser tube is a beam of energy. It's a beam of heat. But the profile of that beam is something like this. The temperature on the outside there may be somewhere where you could touch it. It may well be 50 degrees C. I don't know, because I've never done that. I have put a K-type thermocouple in here and tried to probe this profile. Now I've got as far as here, and at that point there, 1300 C, I melted the end off my thermocouple. So I know that as we get closer to the end here, it gets probably up above 1500 degrees C, because I have melted stainless steel with it, and stainless steel melts at 1450 C. This is a bit of a guess profile, but what it does demonstrate is that there is basically temperature in here, and that temperature gets hotter down the centre than it does down the outside. If I expose a piece of material to the tip of that for a certain period of time, a very short period of time, it's sufficiently hot at 1500 degrees C to put a little burn mark in there. Now, the longer I leave the burn on there, the bigger the circle will become, until eventually you get to the point that I've already proved to you that you can get heat right out as far as this outside edge. If you wait long enough, we can burn a full-size hole in a piece of material. But the critical point I'm making there is it's time related. I have to wait a long time to finish burning that large circle. So that's what's actually happening here with this mark space ratio. We are decreasing the time that the beam is allowed to touch the material, and so consequently we're getting a smaller and smaller burn. Now I've done nothing more than change it back to common mode. I've left all the other settings exactly the same. So I've left all the other settings the same, and I've just changed it back to common mode, 6.4, and that we thought was about 6.5. So they're not far off, but none of them are really different. 50% makes a small difference there, look. Okay, so now I've set up the cutting square, 20mm square, but it's going to cut in dot mode. And dot mode, where I've set the time interval to 1/1000th of a second. So we're looking for a 1 kilohertz signal here. That's the fastest that I can set the time to. We've set the interval to 0.001 of a millimetre, 1 micron, and we've set the actual dot length, 1 micron, 0.001 of a millimetre. Let's see what we get. Now bear in mind these are 5 millisecond intervals across the bottom here. Well, I'm not impressed with that, because basically, look, that's one complete cycle there, and it's not even half a cycle there in 5 milliseconds. So that's about 1.4 cycles in 5 milliseconds. Let's just say 1.4. 5 divided by 1.4 is 3.57 milliseconds per. I mean, that's only 285 hertz, and yet I asked for 1000. Let's put the speed up and see what happens. We'll leave everything else the same. We'll change the speed to 400. Let's go from 25 right up to 400. I'm just looking for the smallest intervals, roughly here. 1, 2, 3, 3 3/4. That equals 750. Still not right, is it? Should be 1,000. Despite my electrical incompetence, the little picoscope is providing us with a lot of valuable information. It's telling us a great deal about this machine, basically how simple it is. I was overcomplicating it with my engineering mind, and yet as soon as I start looking at it electronically, it becomes a very simple machine. Now, I'm yet to understand why changing the mark space ratio on the switch on, switch off is likely to affect the life of the tube. We did not drive the current over, as I was half expecting to see. The current was always totally inside the working range that we were going to use for the machine. Every time the tube fires, it passes through this pre-ignition zone, which we've called high frequency impact engraving, but basically it's a pre-ignition zone where you get incredibly high frequencies and incredibly high currents for incredibly short periods of time. I would have thought that was more likely to do damage to the tube than what we've seen today. But perhaps there are some physicists amongst you that can answer that question. I'm not competent to do so. It's just that logically I can't see that I've done anything wrong there that's going to shorten the life of my tube. Now, whether or not it'll have any gross effect on the flatness of my bottom, in my 3D engraving I mean, I'm yet to find out, but that's something we can check out on another session. So for today, thanks again for your time, and I shall see you next time.